All right, so the next portion, like I said, let's do our parallel circuit calculations. This is probably the most in-depth portion of the test. And there's quite a few problems here. And what I tried to do is they'll kind of give you a scenario. I tried to pick 3 or 4 or 5 problems about the same scenario. And the reason I tell you that is, okay, so one question might say, okay, here's a parallel circuit. What is the amperage of load 1, or what is the resistance of load 3? Which is kind of a daunting task to find that one item. But solve for the whole problem right off the bat, because odds are you're going to solve for the whole problem. You're going to need all or most of those values in future problems. And that's why I did that. I didn't want you to have to do all this work to find one value. I'm okay with you guys doing a lot of work, but let's make it worth our, the bang for our buck here. So again, as you guys know, and hopefully you remember, is I like sort of this grid method here, right? We have a column for total values for the whole circuit. We have, in this case, we have a 3 load circuit, load 1, 2, and 3, and then we've got volts, amps, ohms, and watts across there. So first of all, we have our Ohm's law. We're still going to use Ohm's law to help solve this, but we also need to recall our parallel circuit rules, right? Our voltage is going to be equal at all points in the parallel circuit. Amperage is going to be additive in that parallel circuit, right? So it adds up, all the loads add up. Resistance is this big, terrible formula. I'm going to show you once again a way to avoid that formula because it's terrible, it's difficult, it's complicated. You're going to make a mistake. And then our wattage is just going to be additive here once again. So here we have a circuit here, right? In this case, they tell us the source is 120, and then all these loads are going to be connected in parallel. On the test, there'll probably be a diagram, a picture. But here we have load 1 is 2,000 watts if operated at 125 volt. Load 2, 5 amps if operated at 120 volt. Load 3, 1,500 watts if operated at 110 volt. So right off the bat, can we do anything? Can we fill anything out? Yes, we can always load in here our source voltage, right? They've got to give that to you every time. Otherwise, there's no way to solve the problem. So your source voltage is always going to be your total voltage, right? So we can, it's kind of like your free space, right? You can always throw that right there in the total voltage. They got to give that to you. Now, what's so great about a parallel circuit calculation is this little formula right here. E total equals E1 equals E2 equals E3. That means we can go ahead and throw that voltage straight across into all these grids, right? So we've just filled in an entire line or entire row of the table with one value. Okay, so at this point, we kind of have a unique situation here. We don't always have this instance, but in this case, load 2, right, is 5 amps if operated at 120 volt. Well, guess what? We're going to operate it at 120 volt. Whenever we're operating a load at its rated voltage, we will get its rated amperage and wattage out of it. So I can go ahead and plug in this 5 amps for load 2 because I'm going to operate it at 120, right? We don't always have that luxury, but in this case, we do. I'm not going to put the unit in there. So yeah, we've got our 5 amps there. We can't always do that, but again, we're operating it at its rated voltage. Go ahead and use the rated amperage. Throw it in there, no problem. Now we can't do that with these wattages because we're not operating this one at 125. We're not operating this one at 110. So we basically have to throw these values away, essentially. So really the only thing we can do at this point is calculate the resistance of, and again, if this wasn't operated at 120, we'd have to calculate this resistance anyway. We're going to do that regardless here. But we can calculate the fixed resistances of all these loads. Once again, that hopefully isn't a surprise, and hopefully you're tired of hearing me say that. So in this case, we know watts, we know volts. We're looking for ohms. We're going to say E squared divided by P. So we're going to do 125 squared divided by 2,000. Gives us 7.813. Okay. Next up, we can use our amps and our volts to find resistance here on this guy. So that's going to be E divided by I to give us R. So we're going to say 120 divided by 5. We get 24, right? And then lastly, we have to do load 3, which is, once again, we're going to say E squared divided by P. 110 squared divided by 1500. 8.067. Okay, so what we could do, we can find total resistance with this formula. I don't want to do that. I told you guys we're not going to do that. Frankly, I don't even know if I'm up for the challenge right now. What else could we do? Well, your goal in this is basically to find two values in any column or all columns. And at this point, we've done that for these three columns, the individual load columns. We have volts and we have ohms in all columns. Let's go ahead and find out our amperage for these missing two columns here, right? So we're looking for amps. We have volts, we have ohms. We're going to say E divided by R is going to give us I. And again, now we're using these values. Forget about these values at this point. We're all down here, right? So we're going to say E divided by R. So 120 divided by 7.813. We get 15.359. Okay. Next up here we have, once again, we're going to be E divided by R, 120 divided by, oops, I want to put it there, sorry. We're going to say 120 divided by 8.067 is going to give us 14.875. And, you know, let's just check, right? Because we didn't calculate this 5. Remember, that was given to us. But we should be able to say E divided by R should equal 5, right? What do you know? It does, right? So there's all these checks that are sort of built into this thing that we can use. So at this point, we've kind of opened the door a little bit for ourselves, right? We can now find these P values using Ohm's law. That's easy. But we can also find I total, right? We have this formula. I total equals I1 plus I2 plus I3. So I can go ahead and add I1, I2, and I3 all up. So we'll say 15.359 plus 5 plus 14.875. We're going to get 35.234. This is kind of a ridiculous circuit, to be honest, but again, I kind of pulled it out of thin air, so these numbers will get a little wacky, but we'll get there. So again, we could, use the total resistance formula, but I don't want to do that. Let's use instead, we have two values. We can use Ohm's law to find this value now. I have E, I have I, I'm looking for R. E divided by I equals R. Well, that's easy, right? A heck of a lot easier than this. So I can say 120 divided by 35.234. We get 3.406. Okay, so at this point we can kind of do another check here, right? On a parallel circuit, it almost seems counterintuitive, but your total resistance is always going to be it always should be the lowest value. Reason being, each one of these resistors lets a little bit of electricity through. Combine them all together, and they let more through than any one would individually. Remember, resistance is opposition to current flow. The more current that flows, the less resistance there is. Well, your amperage, since it's additive, mathematically has got to be higher than any one of these. So your current's higher, therefore your resistance must be lower. So your total resistance in a parallel circuit will always be the lowest value. If it's not, you made a mistake, right? So again, we have a nice little check here built in. At this point, we really, there's only a couple things we can do. We can find the power value, the wattage value using Ohm's law for all these columns here. We could find this one, and this one, and then add these three up to get this one because of this rule here. However you want to do it, you should get the same result. It should not be an issue. So we're going to go ahead and we're going to say, I like to use E times I. It's one of the only ones I really have memorized, to be honest with you. But P equals E times I, right? Pretty easy. Pretty straightforward. So we're just going to do E times I for each column here. I'll save this one till last. I don't know why. Doesn't matter. So 120 times 15.359 will give us our L1 value of 1843.08. Here again, we'll do 120 times 5 to give us this value here. So we'll say 120 times 5 gives us 600. And then we'll say 120 times 14.875. We get 1785. Okay, and then last, but again, we could add these up. We could do E times I again. Doesn't matter. You should get the same answer, assuming everything was done correctly here. We're going to get 4228.08 watts. So we've got a couple other little checks we can do here, right? So L1, if operated at 125, should give us 2,000 watts. We operated a little bit lower at 120. Our wattage goes down a little bit. That makes sense. That's what we expect to see. Load 3, if we operated at 110, we should get 1,500. But we operate a little bit higher at 120, and we get 1785. So the wattage goes up a little bit. So there again, that all makes sense. That checks out, right? So we're pretty good with all these answers here. But again, the procedure is, on a parallel circuit, fill in your voltage total. That can carry through to all these voltage boxes as well. Now we're going to find fixed resistance using Ohm's law of our given values up here. Plug those in for each load. You could find total resistance. I don't like to do that. Use Ohm's law. Find the other values here, right? Now we can use this rule, I total equals I1 plus I2 plus I3, to give us total amperage. We could do the same exact thing for our power row down here. So there's your parallel circuit rules. Remember, use these 4 rules, use your Ohm's law, find that fixed resistance right off the bat. So next video, we'll wrap this thing up. We'll do burial depths and we'll do wire sizing, and we'll get this thing out of here.